and welcome to Hands on Arduino Part 5. Here we're going to talk about some examples of using SPI communication. We're going to start simple and we're going to go up from there. So let's begin. Here we have an example of using SPI communication. We have an SPI master and we have 3 slaves. So SPI communication is bidirectional communication. And if you notice, there is a master out, slave in, master in, slave out. 2 different communication lines, one going one direction, the other going the other direction. Both of these lines are connected to all the slaves. In addition, the clock is connected to all the slaves, and each slave has what's called a slave select line, which is active low. So the master, the number of connections to the master is related to the number of connections to the slaves. So in other words, these 3 lines, the clock, the master out, slave in, master in, slave out, those are common. So those 3, and then you have a line, slave select line for every device. You can simplify this if you have, for example, if you're only communicating to one device, you don't have to use the slave select since it's understood that you are only communicating with one other device. SPI specifics. So it is synchronous. That is, there is a clock that may be set to arbitrary rates, unlike standards like RS-232, where there are certain baud rates that you have to use. This is ideal for microcontrollers that might have an imprecise clock. The clocking doesn't have to be extremely precise. Basically, the data, the next serial bit is transmitted on every rising edge of the clock. So whenever that is, that's when the data is transmitted. So basically, the master controls the clock. No clock, no data transfer. The slaves are controlled by the master clock. And the slaves cannot manipulate the clock. So basically, that's what we have with the clock. So how does the SPI communication compare with the I2C communication? Well, here are some examples. So this is a full duplex communication scheme. That is, it can communicate simultaneously, unlike the I2C communication, which sends, the master sends one block, the slave sends a block, and it's back and forth. That's not true bidirectional or full duplex. Okay, so as a result, it has a higher throughput than either I2C communication or the SM bus communication. I'm not going to talk much about the SM bus. Arbitrary message sizes, arbitrary content, arbitrary purpose. These are defined by the devices to which the communication happens. So, in other words, I don't always have to send out a byte of data. I could send out as many bits or as few bits as I want. If I just want to send out 3 bits, I can just send out 3 bits, so forth. The interfacing is fairly simple, like the I2C. Not quite as simple as the I2C or the 2-wire communication, but it is definitely more simple than, for example, RS-232. In general, lower power needs than either I2C or SM bus. So the bus, for example, doesn't need to be powered. It's just you just have the different lines. No arbitration needed. Because of the fact that the master communicates with the slave through a slave select line, the slave and the master only communicate when that slave select line is activated. Otherwise, the slave will neither receive nor send. And so there's no arbitration needed. It's done by the slave select line. Again, all the slaves use the master's clock. Slaves do not need a unique address, and you can use unidirectional. Each of the signals itself is actually unidirectional. The communication from the master out, slave in, master in, slave out, the direction of the communication goes only one way on those lines. But it does require more lines in general than I2C communication. Some disadvantages are that in general requires more pins than I2C, no hardware flow control by the slave. The slave cannot control things. No hardware slave acknowledgement to communicate that the slave received the data properly. It supports only one master device. No formal standards. So the standards are not nearly as clear, and so you can have some sloppy things happening. In the SPI library, there are some pins that are predefined. The clock, SCK, is defined to be pin 13. Slave select is defined to be pin 10. Master out slave in is defined to be pin 11, and master in slave out is defined to be pin 12. And this is true for the Arduino or Due Milanova. For the Due or some of the other Arduinos, you'll have a different setup, so anyway. But this is what it is for the Arduino. I should say Due. I'm sorry, Arduino Uno or Due Milanova. The ICSP header has these connections established that can be used for SPI communication. So, in a sense, the Arduino provides more hardware support for SPI communication than for I2C communication. This header is such an example. In the SPI, there are different data modes. Now, if you're working at the low level, then it's important to understand all of these possibilities. But if you're working at it using a library, this stuff doesn't make much difference. In terms of the library setup, these are some of the options that you can set up. You can set up the bit order, whether you're doing least significant bit first or most significant bit first. So that is, you're going to send out a serial packet, and so the question is, which order are you sending the bits? Most significant bit first or least significant bit first? You can select that. The mode is SPI set data mode, and you have the different modes, and these modes again come back to this setup. So you can pick them if you want. There is one defined already, predefined. I believe that's mode 0 is the one that's the default. You can also set up the speed. So I believe there's already a speed set up. I don't remember which of these it actually uses, but you can choose the speed at which the transmission occurs. You choose the speed by choosing the divider. So if you want it slower, you would use a larger divider. Otherwise, you would use a smaller divider. So, and you have a number of options. Well, those are the basic characteristics of the SPI communication. Let's get into some detailed examples. First example, I call it Breakout. Breakout, we're going to communicate serially to a device, and that device is going to break out the serial data and show it in parallel. Okay, so it's going to take a byte of data and it's going to show all 8 bits using LEDs. So that's the idea of Breakout. It's going to break out the serial data into parallel data. So let's take a look here. Here's the circuit. So in this case, we only need the clock and the master out slave in. We don't need a slave select because we're only having one device, and we don't need the master in slave out because it's only communicating one direction. So ordinarily you need at least 4 pins for SPI communication, but in this example we actually only need 2 data pins, and then of course we need ground to connect everything. In our case, the grounds basically are part of the twisted pairs that we use for this example. The twisted pairs basically are used to help, again, provide some at least minimal level of shielding against noise. In our example, I'm going to use a pair of twisted pair cables, and they're about 2 meters long, 6 feet roughly. So that gives you the idea that you can go a certain amount of distance, and of course, the longer distance you go, the more likely you are to have communication difficulties. But at this distance, it's not a problem. Communication goes fine. So here I can connect these lines directly up to the Arduino. On the other end, I have a breadboard with a 74LS164 chip, which is a serial to parallel chip. Now this serial to parallel chip basically has a number of connections to it. So one of the first two connections here are the data, that is the serial bits coming in. Associated, so that's one of the data lines. So notice here, that actually should be connected to pin 11. It should be connected to pin 11, not pin 12. But that's the data. Okay, that's the master out, slave in. And then the red line here is the clock, and that goes over here to this pin over here. The chip requires ground and power, and so this little thing is going to be used to provide the power. It's just a power supply connection that gives 5 volts and ground. Okay, so there's 5 volts and there's ground. So this bus on the breadboard is ground, and this bus on this other side is 5 volts. Okay, so notice that on this connection here to 5 volts, this is on the chip that has the connection called clear, and it's clear active low. So active low means that if I ground that connection, it will clear the outputs. So I don't want that. I want the outputs to remain to go out, and so I just pull it high. Okay, and then the other connections, the other 8 connections. So this is the other 8 connections all connect to LEDs, a bank of LEDs, and they basically go from 5 volts through these resistors, through the LEDs, and then they connect directly up to this chip. So basically what happens is when one of these channels goes low, it basically grounds one side of the LED and allows the current to flow. So in a sense, these outputs are active low. Okay, so if I want to turn on one of the LEDs, I need to actually pull the particular channel. I need to pull it low. Okay, so that's important in understanding what needs to happen when we do the code. So you can also drive LEDs with directly with the output, but it's a little more tricky, and in general you can get the light to be a little brighter if you do it this way, as opposed, because generally the chips, TTL chips, cannot source that much current. They don't source much current, and so you don't get as bright a light as if they can sink more current. That is, they can take current to ground easier than they can source current. So we use that feature of the TTL chip in driving these LEDs. So this is the circuit that we're working with. And so basically what we're going to do is we're going to send out a byte of data from the Arduino. Basically this is what's called a shift register. And what it's going to do is it's going to take bit by bit and it's going to shift it in. The first bit that comes in gets shifted into the first slot. The next bit of data shifts over, and then so the next bit comes in, and so the first bit actually goes through each output as the next bit comes in until all 8 bits are in. Okay, so that's basically how it works. So if one of the bit is set, it'll actually go all the way across, and it'll actually light up every LED as it goes across. But it all happens fairly quickly, so you don't see the lights flashing. In some configurations, people have reported seeing the lights flicker a little bit when a bit goes by, but in many cases, depending on how you set the resistor values, you may or may not get any flashing. So this is the circuit that we're working with and our problem. We're now going to look at the code to see how the code works here. So here's our setup routine, and basically we're going to set 2 pins to be outputs. So pin number 13, pin number 11, so that's the clock and the master out slave in. Okay, so we've set those up. And that's all we need as far as setup is concerned. We don't have to set baud rates or anything. Everything else is predefined. So this is like the very simplest SPI communication. Very simplest. It is just doing the bare bones things, and some of these things are already predefined. For example, SCK is predefined as pin number 13. MOSI is predefined as pin number 11. So I don't actually have to define SCK or MOSI. It's already predefined in the Arduino IDE. In fact, if you try to define SCK, it's going to barf. It doesn't like that. So that's our setup routine. Our loop routine, basically I have broken up into 2 parts. Okay, so each part is similar. We basically go from 0 to 7. Okay, and what we do is we take this number 0, 1 and we shift it by k. So the first time we shift it by 0, which means it stays in that location, and then that 1 just moves across. Each time through the loop it moves across 1. Okay, and so notice that I have a 1 in all zeros. When the bit gets shifted, a 0 gets put in the new place. It gets shifted over. The last bit gets shifted out, and 0 gets shifted in. And so basically I'm going to have all zeros and a 1 depending on where that thing, and the 1 is wherever that thing is shifted. Now, if you recall, in terms of our circuit, in order to light up an LED, I need the bit to be a 0, because remember, it's active low. And so if I only want one LED lit and all the rest dark, then I actually have to do the logical, or not the logical, but the bitwise not of all of that. Okay, so that's what this is doing. And here I've chosen to do least significant bit first. I could have done most significant bit first, depending on where I want to start this. So basically what's going to happen is the LED is going to move all the way across. So the light is going to turn on, the next one's going to turn on, this one's turned off, and so forth, all the way across. And then the same thing is going to happen again. So notice this time it's shifting right instead of left. So this thing basically is going to shift right, shift left, shift right, shift left. And I have a small delay in between. Okay, so some people prefer to use a TTL chip that has what's called a latch associated with it that actually holds the data constant and prevents that flicker that I was talking about. Some people prefer that. If you have the problem of flickering, then you may want to consider something like that. But it comes at the expense of requiring an additional bit. That is, remember we only needed to use 2 pins. We needed to use the SCK and the MOSI. If you want a latch, then you require a 3rd wire, and that adds some additional complexity to the whole problem. So this is the code that we're going to use. Now let's take a look at the hardware, the actual hardware. Here's the code we're working with, and I'm going to go ahead and download this to our circuit over here. So click on this, and once it's running, you should see the lights starting to light up, and you can see it's going back and forth just like we had designed it to. The one light is going back and forth. So each time you see that light having moved, that means another bit of data has actually been sent out through the serial port. And so you can see that we have this delay of 50 milliseconds. And so basically each LED is lit for only 15 milliseconds before moving on to the next bit. And so we can see it works. Pretty sweet. So I get this little light dancing back and forth. That's kind of fun. So this is the first example of SPI communication. Well, I'm going to go and do some more demonstrations using SPI communication, but I'm going to reserve those for a next video. I was hoping to get that into this video, but I think I'm going to go ahead and include that in another video. But before moving on out of this video, I just want to mention something about cable. I've already shown you the use of twisted pair for doing communication. Well, it turns out that twisted pair is a very common means of shielding cables from unwanted interference. Another form of cable that is very commonly used is what is called twisted pair cable, but in this case it's a specific kind of twisted pair cable. I'm going to show you what's called a Cat6 cable and show you a little bit of its features, and in the next video I'm actually going to use this Cat6 video to do communication between Arduinos and so forth. So Cat6 cable basically has a set of twisted pair wires inside the cable so that you can use it. Now, another thing I want to show you that's really helpful is this little tool. This is a handy little tool for working with cables. An electrician friend showed me this tool. And the tool itself, you may or may not be able to see it, but there's a little knife blade inside that hole there. And that knife blade is really handy for being able to strip cables and to be able to slice the jacket in a way that you can easily get to the cable. So now, as I said, this is a Cat6 cable. This Cat6 cable has certain features to it. Let me show you what the features are. First of all, there's the outer jacket. That's this plastic insulation that's there. Then around all the cables is what's called a shield. So this shield is foil wrapped around the all the twisted pairs. Okay. In this case, this Cat6 cable has 4 sets of twisted pair cables. In addition to the shield, the foil shield, there's also what's called a drain wire, which is just a wire that goes along with the shield, and that helps again prevent interference. So basically what happens is on one side of your circuit you would ground this, and that would provide like a grounded shield around the cable for the entire length of the cable, and that helps prevent unwanted electromagnetic interference from getting into the cable. Now this particular cable also in addition has a plastic wrap around the sets of twisted pairs. I don't know why, but anyway, it does. I suppose that's to help in case the wire bends and bends and bends and bends, and maybe some of the wire kind of starts poking its way out of its own insulation, and that way it doesn't poke into the shield. I'm guessing. The next thing we have is we have, as I said, 4 pairs of twisted pair cables. So each pair has a different color. Each pair has a white wire and then a colored wire. The white wires are usually used as ground. So in addition to having the ground for the drain wire and the foil shield, you also have a ground associated with each signal that's being communicated. So the Cat6 cable is useful in being able to have 4 signals transmitted. Now, theoretically, because there are actually 8 conductors, you could actually communicate 8 signals. However, because of the fact that you want to keep these signals from crosstalk, so crosstalk means that one signal communicates with an adjacent signal. That is, when this guy is pulsing, this guy next to it picks up those pulses. And generally speaking, you don't want that to happen. You want each signal to be completely independent of the other signals. And so that's the whole purpose of all this. In fact, if you look carefully at the various twistings of each of these pairs, they're all twisted a little bit different. So for example, this blue is very tightly twisted, whereas the brown has fewer twists per inch. And again, that is purposeful in that it helps to reject the crosstalk. Also, this particular cable in the middle has like a little divider thingy, a little plastic divider that divides all 4 channels. And as you can see, if you look closely, that divider is actually twisted. So you not only have each pair twisted, but all 4 basically are twisting as they go along through the entire length of the cable. So quite a lot of stuff going on in this little cable. So I'm going to use this baby for the experiments that are coming up in using the SPI communication, because with SPI communication you have more information or wires that are needed than with I2C communication. Remember, I2C is also called 2-wire interface. Well, SPI communication requires more than that. And so it's helpful to be able to have a nice cable that is shielded from noise in the communication process. So, well, that's all for this presentation. Come back next time for the more presentation on SPI examples. This is Hands on Arduino. Thanks for watching.